Welcome to the camera section of the course, and in this section we'll be covering everything camera related in V-Ray. And if you have a photographic background, this section should be a piece of cake for you, as every concept here is based on a real world situation. In this particular lesson we'll be covering physical camera. V-Ray had its own physical camera for a long time, but from 3ds Max 2016 there is a 3ds Max physical camera that is fully compatible with V-Ray, and it actually was co-developed by Autodesk and Chaos Group. And now 3ds Max physical camera is the main camera you use to render your scenes in V-Ray. But if you open up an older scene that was utilizing V-Ray physical camera, you would have no problem, and there is actually a way to create the old V-Ray physical camera if you fancy that. But for now, let's focus on 3ds Max physical camera. You can add a physical camera from the V-Ray toolbar, command panel, or the menus. I tend to use V-Ray toolbar to add the camera. So let's click on this physical camera icon in the toolbar and click and drag in the viewport to add a new camera. Now press Ctrl C so the camera adheres to the current perspective view. We are still in the perspective view, so press C to view the scene through the new physical camera. Now as you can see, a new physical camera has been added to our scene. Select the camera and go to the modify panel and see what we have here. In the basic rollout, the first option we have is targeted, which is enabled by default, and in this case if I change the view to a quad view, you can see the camera has a target object. We can select the target in the Explorer and move and transfer our camera around, and if we disable it, the camera would be a free camera. Next we have target distance, which basically sets the distance between the camera and the target or focal plane. And if we take a look at the focus section right now, the focus point or focal plane of our camera is based on the target distance. Let's say I want the focal plane of the camera to be on this chair here. Possibly something like 500, maybe 35 centimeters would be enough. In the viewport display section, we can decide when we want to see the camera's cone in the viewport. By default, it's set to when selected, so only when the camera is selected the camera's cone will be visible. If set to always, it will always be visible whether the camera is selected or not, and if set to never, it will never be visible. Let's set it to when selected. We have show horizon line, and if I hide all my geometries and enable show horizon line, we get a black line which represents the horizon line in the scene. It can be useful sometimes. Let me disable it and unhide all the objects in the scene. In the physical camera rollout and in the film and sensor section, first we have preset, and here you can define your film or sensor size, and we got full frame, APS-C Canon, APS-C Nikon, APS-C H, 4/3, and custom, where you can set the sensor size manually down here using the width parameter. In a digital camera, sensor is the very heart of your camera. It determines the final resolution of your image, its size, how good your camera performs in low light situations, the dynamic range of your photo, and obviously the larger the sensor, the better the quality of your photo, and full frame sensor is the largest sensor. But in CGI it really doesn't matter that much. Maybe if you are trying to match your camera to a live action camera or a photographic plate, this option can be very useful. I mean, sensor size is extremely important, and possibly the first thing you look for if you are buying a new camera. For example, you're going to get much shallower depth of field if you are using a full frame camera like Canon 5D Mark III compared to a 4/3 camera like Panasonic GH4. But here the sensor size is not as important as real life. In the lens section we have focal length, which is the focal length of the lens, And basically focal length determines the angle of view, how much of our 3D scene will be visible in the render, basically the overall magnification. The longest or higher the focal length value, the narrower the angle of view, and the higher the magnification. And the shorter the focal length, the wider the angle of view and the lower the magnification. So if we start from a short focal length like a 10mm lens, you see we have a very wide angle of view, and as I make the focal length longer, we would have a narrower angle of view and higher magnification. Let's try 18, 24, 55, 85, 135, and 200. Let's use 18mm for now. Next we have specify field of view. When on, lets you set a new field of view value in degrees and allows you to control your focal length in degrees, which might be easier for some people. So if we want to achieve longer focal length, we can use narrower angles and vice versa. And as I'm changing the angle here, you can see the focal length is getting updated. So while specify field of view is on, the focal length control is disabled. However, changing the value of one of these controls also changes the value of the other. Let's disable specify field of view and set the focal length to 80 for now. Zoom basically zooms the lens in or out without changing the camera's position. This option provides a way to crop the rendered image without altering any other camera effects. I mean, if I set the zoom factor to 2, we are going to have the same field of view as setting the focal length to 160mm. But changing the focal length changes the depth of field effect because it changes the aperture size, while changing the zoom value does not. So if we increase our focal length to 160, the depth of field will be shallower, but if we increase the zoom factor to 2 to get the same result, the depth of field will be the same as before. Next we have aperture, which sets the size of the lens aperture as an f number or f-stop. The f-stop changes the aperture of the lens. A smaller f-stop number like 2 means the aperture is more open. A higher f-stop number like 16 means the aperture is more closed. F-stop affects two things. First, exposure, and second, how shallow or wide depth of field effect is. We are gonna be talking about depth of field in our next lesson, but for now we are only focused on how the f number affects the exposure. A smaller f-stop number means the aperture is more open, therefore more light is gonna reach the sensor and the overall image is gonna be brighter. And a higher f-stop number means the aperture is more closed, so less light is reaching the sensor and therefore darker overall image. Right now, because in the exposure rollout, the exposure method is set to target, which we'll be discussing in a moment, f number doesn't affect the exposure. It only affects the depth of field and how narrow or wide it is. For now, let's set the exposure to manual. Now f-stop, shutter speed, and ISO control the overall exposure. Let's take a look at a few renders with different f numbers. In the first render, f-stop was 1.4, and because the aperture is wide open and more light reaches the sensor, we get a very bright and overexposed scene. In the next render, f-stop was 2.8, then 5.6, then 8, 11, and 16. As we can see, by increasing the f number and closing the aperture more, each time we get darker and darker renders. In this case, f-stop of 8 results in a well exposed image, I guess. So let's make sure F number is set to 8. Using the focus section, you can define distance for the camera. By default, it's based on the target distance, which we discussed earlier, or you can set it to custom and define your own focus distance manually. Lens breathing adjusts the field of view by moving the lens toward or away from the focus distance. A lens breathing value of 0 disables this effect. And we have enable depth of field, which allows you to enable or disable depth of field effect. We'll be discussing depth of field in detail in our next lesson. For now, let's continue with the rest of the parameters. We have shutter or shutter speed section. The shutter is a light occluding piece of metal in front of the camera sensor to block light from reaching the sensor all the time. When you take the photo, the shutter is moved out of the way to expose the sensor to the light. Then it is moved back again in front of the sensor. The speed at which this is done is shutter speed. The faster it is, the shorter time the sensor is exposed to light. So if you have dark interior scene, for example, you need to use a long exposure or longer shutter to avoid an underexposed render. But for a daylight scene, you need a much shorter shutter speed to avoid an overexposed render. Shutter speed also controls motion blur, which we discussed in its own lesson. In the shutter section, first we have type, and here you can define which unit to use in measuring shutter speed. We have frames, which is typically used in computer graphics, second or fractional seconds, which are typically used in still photography, or degrees, which are typically used in videography. I personally tend to use fractional seconds, so let's use that. And we have duration, which sets the shutter speed, basically how long the shutter would be open. Let's take a look at a few renders with different shutter speed durations. The first render was done with the shutter speed set to 5,000th of a second, and because shutter is open for such a short time, the render is underexposed and very dark. In the next one, shutter speed was 1,000th of a second. The shutter was open longer, so the sensor was exposed more to light, and we get a brighter image compared to the first one. Then it was 100th of a second, then 50th of a second, and finally 10th of a second. In the last render, because the shutter is open for such a long time, we get an overexposed render. In this case, the render with shutter speed of 50th of a second is well exposed, so let's set the duration to 50th of a second. So up to now, we know that when the exposure gain is set to manual, both aperture and shutter speed affects the exposure of the render. And as we'll learn in a moment, ISO also affects the exposure in this mode. In the shutter section, we have offset. It specifies when the shutter opens relative to the start of each frame, and it affects motion blur, which we will be discussing in its own specific lesson. And finally, we can enable or disable motion blur, which, as I mentioned, will be discussed in detail in a later lesson. In the exposure rollout, first we have install exposure control button. If enabled, by clicking it, it would make the physical camera exposure control the active exposure control in the scene. But if it is already active, the button will be grayed out like now and reads exposure control installed. In the exposure gain section, we have two modes to control the overall exposure. In the manual mode, the exposure is dependent on aperture size, shutter speed, and the ISO value here. But in the target mode, which we'll learn about it in a moment, only this single exposure value here is responsible for the overall exposure, and aperture and shutter speed control only depth of field and motion blur. ISO is film sensitivity to light. A higher value means more sensitivity, therefore brighter render, and a lower value means less sensitivity, therefore darker image. Now let's try a few render with different ISO values. In the first render, ISO was 100. Then 400, and finally 1600. As we increase the sensitivity, we get brighter images. But controlling the exposure with aperture, shutter speed, and ISO is not very easy. And at the other hand, it's going to cause some limitations when working with depth of field and motion blur at the same time. So that's why we have this target exposure mode. In this mode, the EV, which stands for exposure value, is the only value controlling the exposure. Higher values produce darker or less exposed renders, and lower values produce brighter or more exposed renders. In this mode, the shutter speed, duration, and the aperture size won't affect the exposure at all. They are just responsible for motion blur and depth of field effects. And also, this is the default mode and my preferred exposure mode as well. The proper EV value is different based on the type of the scene you are working with. Something around 10 would be good for a daylight interior render, something from 13 to 15 for a sunny daylight exterior, and something like 6 to 8 for a studio setup would probably work. Now let's try a few exposure values. In the first render, the EV value was set to 6, and as you can see, the render is a bit overexposed. Then it was set to 8, then 10, then 12, then 14, and finally 16. As we can see, by increasing the EV value, the scene gets darker and darker. For this lighting, I think an EV of 10 would probably give the most well exposed render. The rule is very simple here. Each time you decrease the EV value by one stop, let's say from 10 to 9, we double the scene exposure and make it twice as bright as before. And each time we increase the EV by one stop, let's say from 9 to 10, the render gets twice as dark as before. Let's set the exposure value to 10 here. Next we have white balance section or group. Basically the lighting condition and the color of the light sources can affect the color of your objects in the scene. We as human beings can compensate for that and actually see the white objects as white in any lighting condition. But in 3D applications and digital cameras, we need to adjust the white balance so that white objects in the image appear white and therefore all other colors in the image also display correctly. And also, you can use white balance to add a certain color cast to your render if you want to. We have 3 ways of setting and adjusting our white balance: illuminant, temperature, and custom. In the illuminance mode, there are some presets based on standard light sources. In the temperature mode, the white balance would be based on a temperature in Kelvin degrees. And in the custom mode, you can choose any color you want to adjust the color balance. By default, it's set to illuminant and it's using daylight preset, which corresponds to 6500 degrees Kelvin. In kelvins or K, the lower the temperature, for example 3200 K, the more red the light will be, and the hotter it is, for example something like 9000 K, the bluer the light will be. Now if you take a look at the presets, you can see, for example, we have incandescent 3200 K. Obviously an incandescent light source will cast a very warm reddish light that makes the white colors to look another color in the photo taken by a camera or in your renders. Unless this is something that you want, you can white balance the scene by setting the preset to incandescent 3200 K, and by doing so we cast out that warm red color temperature and white balance the scene. If you are in a natural daylight lighting, you can set the preset to a neutral daylight 6500 K. If you are under very hot warm sunlight and there is some yellow color cast in the scene, you can use sunlight 5200 K preset to make the whites whites again by casting out the yellow color produced by the camera. By the light source. If I go to the frame buffer and load the render with EV set to 10 and also enable my correction tools and enable white balance, If I want to make the scene cooler, we need to cast out some warm tones. So we set the temperature to a hot temperature like 5000 for example. Now the render looks bluer and cooler. And to do the opposite, we just need to set the temperature to a higher one like 8000 to make the scene look warmer and cast out some cooler tones. Now let me show you a few renders with different presets. The first render was done with a daylight 6500K preset, which is the default preset. The next render was done with sunlight 5200K. Now we are casting out warmer tones and getting a cooler image. Next one was done with shade 7000K preset, and now we cast out cooler tone and getting a slightly warmer render. If we take a look at the render with daylight 6500K, because of the dominant blue sky that we have outside, we get a slightly cooler tone than what we possibly want. But in the shade render, we get a warmer render. And in the final render, incandescent 3200K was used, and we get this very blue render. We can set the white balance mode to temperature, and instead of using the presets, use any temperature that we want. Let's set the temperature to something like 9500. Now we are going to be getting a warmer render because we are casting out a cool temperature, and you can see the result in the frame buffer. Obviously, you can set it to custom and pick any color using the custom option. If I select the daylight render again, I can actually use the white balance correction in the frame buffer and adjust the white balance here. For example, let's make the tone cooler by using a warmer temperature, or vice versa. But doing it here is not going to give you the exact same result from the physical camera. For small adjustments, the white balance correction is quite enough here, and it is a correction, and you don't have to render your scene every time to get the correct white balance. In this case, let's set the white balance to temperature and set the value to 7500K, so we get a warmer render and cast some blue out. Next we have enable vignetting, and it means darkening of image corners when compared to the center. So let's enable it and try a few vignetting amount. In the first render, vignetting amount is set to 0, so no vignetting. Then it was set to 1, 2, 5, and 10. For now, let's set it to 0 and disable it. Another way of achieving vignetting is by using optical vignetting in the bokeh or depth of field rollout. This vignettes the frame by simulating the cat's eye effect that some wide-angle lenses can generate. For this to work properly, we need to have depth of field enabled. We're going to be learning more about this effect and depth of field in our next lesson. Bokeh or depth of field rollout will be discussed in the next lesson, obviously. Next we have perspective control rollout. These settings shift the camera view horizontally or vertically without rotating or tilting the camera in both the X and Y axis. We can use positive and negative values here to shift our camera without tilting or rotating the actual camera, which can be useful. In the tilt correction group, you can tilt the camera horizontally or vertically to correct the perspective, particularly in scenes where the camera is already tilting up or down, and to achieve the simulation of tilt lenses for 2-point perspectives. Also, auto vertical tilt correction. When this is enabled, vertical value will be set automatically to align perspective along the z-axis, and it is very useful in exterior architectural visualizations to correct the perspective. In the lens distortion rollout, you can control the lens distortion of the camera. When set to none, no distortion is applied. Next we have cubic distortion. Positive values introduce pincushion distortion. Negative values introduce barrel distortion. In pincushion distortion, the greater the distance from the center of the image, the more lines warp inward toward the center. Pincushion distortion also vignettes the image to a level. In barrel distortion, the greater the distance from the center of the image, the more lines warp away from it. In the first render, distortion amount was set to 0.1 and we get the pincushion distortion type. As I'm using positive and negative values, you can see in the viewport this blue grid, which is from our camera, represents the amount and type of the distortion. But we cannot see the actual distorted image in the viewport. So let's see if you render with pincushion and barrel distortions. So as I said, the first render was done with distortion set to 0.1. The next one, it was 0.2. As you can see, we get stronger pincushion distortion. And finally 0.3. Then to see the barrel distortion, I started using negative values. First negative 0.1, then negative 0.2, and finally negative 0.3. Let's set the amount to 0 for now. Also, you can use a texture to distort the image. For now, let's set the distortion to none. In the miscellaneous rollout, we have clipping plane section. Using this section, you can clip or hide certain parts of your objects from the render view while still having them affect the lighting in the scene. When this parameter is active, two planes are attached to the camera, a near and a far plane. Anything before the near plane will be made invisible in the render, and anything beyond the far plane will be made visible in the render. So only the things that are between the near and the far plane will be visible. Let's try 500 for the near plane, maybe 550, 650. As you can see, anything in this distance from the camera is clipped away. And if I set the far clip to, let's say, 700 centimeters, you can see only the parts of the objects that are between 650 and 700 centimeters are visible and the rest is gone. Let's set the values to 0 and 100,000 centimeters and disable clipping. In the environment ranges group, we have near and far range, and these determine the near and far range limits for the atmospheric effects set on the environment panel. Objects between the two limits fade between the far and near values. And in the V-Ray properties section, we can define the resolution of the bokeh texture, which we discuss in the next lesson, and in the lens distortion group, which allows you to load the .vr lens file generated in the lens analysis utility, which is provided with V-Ray, and you can find this tool in the tools folder of the V-Ray installation folder, and you can use this file to distort your image. Now let me, for the final render, enable vignetting and set it to 2, and we can take a look at the final render. As always, right click on the image and choose load render settings to see the final render settings that I've used for this render. Also, we have a denoiser pass as well. Now we can enable our correction controls and adjust the overall exposure of the render if you want to. Or adjust the white balance. Okay, in this lesson we learned about physical camera. I will see you in the next lesson for the depth of field discussion. In this lesson, we are going to be learning about depth of field. Depth of field basically is the range of acceptable sharpness within a photo that will appear in focus, or in simpler term, the parts of the image that are in focus. If the areas of focus are very small in the image, we have a shallow or a narrow depth of field. You can see in this render in the frame buffer in which the camera's target is on the clock, only the clock is in focus, and as we get closer from the clock to the camera or from the clock to what's behind it, the image gets more and more out of focus and blurrier. And this gradual change from focus to out of focus areas happens very fast. Here we say we have a shallow or narrow depth of field. On the other hand, like our next render, if the areas of focus are very large in the image, we have a wide or a deep depth of field. In this image, you can clearly see a larger area is in focus compared to our previous render. Now, let's see where we can enable depth of field in our physical camera and what factors control the depth of field in your render. Select the first physical camera in the scene. And as you can see from the top view, the camera's target is on the clock. In order to enable depth of field, you need to go to the physical camera rollout, and under the focus group, you can enable depth of field. If disabled, the entire scene will be sharp and in focus. So let's enable it for now. Right now, the exposure mode is set to target, so changing the aperture size wouldn't affect the exposure. The deciding factor on how narrow or wide the depth of field is the aperture size, which is being controlled by the f-stop number or f number. In the previous lesson, and as we can see in the frame buffer, we learned that smaller f numbers means larger aperture size, and larger f numbers means smaller aperture size. Now we need to add another concept here. The smaller the f number means larger aperture size and also narrower depth of field. And on the other hand, the larger f number means smaller aperture size and wider depth of field. Just to simplify this again, the smaller and lower your f number, the narrower or shallower the depth of field. And the larger and higher your f number, the wider or deeper the depth of field. Now let's see a few renders with different f numbers or f-stop numbers. Set the f number to 1.4 for now and take a look at the render with this f number. As we can see, we have a very shallow depth of field. In the next render, f number was set to 2. Still very shallow, but wider depth of field compared to our previous render. Then f number was set to 4. Still shallow, but again wider. Then it was set to 8. And finally 16. When set to 16, you can see we have quite a wide depth of field and most of the scene is in focus. So again, the smaller and lower your f number, the narrower or shallower the depth of field, and the larger and higher your f number, the wider or deeper the depth of field. For now, let's set the f number to 2. The next thing you probably want to know is how to change the focus distance. Right now, the focus distance is based on the camera's target, and the target is on the clock. If we want to make sure the books and the bottle are in focus, all we have to do is to make sure the target is on the books. So let's do that in the top view. Maybe a target distance, something like 152 centimeters possibly would work. Now, if we render the scene, the clock will be out of focus and the books and bottle will be in the focus. There you go. Let's set the target distance to be on the clock again. The exact target, I think it was 1 113.287. In the focus group of the parameters, if we don't want to use the camera's target distance as a focus distance, we can simply change the focus mode to custom and define our own focus distance. Another important factor in how narrow or wide the depth of field is going to be focal length. And the rule here is the longer the focal length, the shallower the depth of field. It's not as important as the f number, but it contributes. I have a second physical camera in the scene. Our active camera right now has a long focal length of 18 millimeter, but we have a second physical camera in the scene which has a short focal length of 20. So let's unhide it and make it the active camera. As you can see from the top view, its focus distance is on the clock. Let me enable depth of field for this camera as well and set its f number to 2. Now, if we render the scene and compare it to the long focal length render, we can clearly see that the camera with longer focal lengths produces shallower depth of field. The first render was done with our second camera, which has a short focal length of 20 millimeter. We get a shallow depth of field, but compared to our next render, which was done with longer focal lengths, its depth of field is wider. Now let's hide our second camera and go to the first camera again. Another important factor in depth of field is the scene scale. Basically, the smaller your scene and your objects, the shallower the depth of field, and vice versa. Let's go to the bokeh or depth of field rollout and see what other options we have. Bokeh, if technically defined, is the quality of out of focus or blurry parts of the image, or simply the pattern exhibited in areas of the image that are out of focus. In the bokeh rollout, first we have aperture shape. When parts of a photo are very much out of focus, the blurred highlights in the photo tend to take on the shape of the lens aperture. Right now the aperture shape is set to circular, so the out of focus highlights will have a circular shape. But if I select bladed and set the blades to 3, now we're gonna have a triangular aperture, which result in a triangular out of focus highlights. Instead of using only circular or bladed types, you can set it to custom and define your own bokeh pattern. If you want to get the same result as the circular type by using the custom texture mode, for example, we would have used a white circle that fills a black background. So you can create your own shape on a black background and use it here as a bokeh texture. Now let's see a few renders with different aperture shapes. In the first render, the aperture shape was circular and we get circular out of focus highlights. In the next render, aperture shape was set to bladed and blades number was set to 3, and we get this rectangular out of focus highlights. Then the blades number was set to 4, and we have a rectangular out of focus highlight. And finally, blade number was set to 5. Also, we have this rotation value, which allows us to rotate the aperture and therefore rotate the out of focus highlights. Let's set the blades number to 3 and see how the rotation works. In the first render, rotation was 0, and in the next one it was 120 degrees. And as we can see, we have rotated the out of focus highlights. We have effect exposure. When it's enabled, the custom texture affects the exposure of the scene depending on the transparency of the texture, and when it is off, the texture always admits as much light as through a circular aperture. For now, let's set the shape to circular. Next, we have center bias. This parameter biases the transparency of the aperture toward the center with negative values or the edge with positive values. Positive values increase the amount of blurring in out of focus areas, while negative values decrease the blur. Now, in the first render, center bias was -50. As you can see, we have a very wide depth of field. Then it was set to 0, which is the default and our normal render, and finally it was set to +50, which produces this beautiful ring effect in the out of focus highlights for now, and also, as you can see, makes the depth of field shallower. For now, let's set it to about 0 here. Next, we have optical vignetting. This parameter, as we discussed in the previous lesson, vignettes the frame by simulating the cat's eye effect that some wide angle lenses can generate. In the first render, optical vignetting was 0, then 2, and finally 3. Negative values for optical vignetting would produce the same result as positive values. Next, we have anisotropy or anamorphic lens section. Here you can simulate an anamorphic lens by stretching the aperture vertically, negative values, or horizontally, positive values, and therefore stretch your out of focus highlights. In the first render, anisotropy was set to -0.75. The effect is a bit exaggerated here, but you can use smaller values to get more realistic anamorphic effect. As you can see, the bokeh is vertically stretched. And in the next render, anisotropy was set to 0, so our normal depth of field without stretching, and finally +0.75, which stretches the bokeh in a horizontal direction. Let's set the anisotropy to 0 for now. And if you want to have depth of field without using physical camera, if you are, for example, rendering from the perspective view, you can do so in the render settings. In the V-Ray tab under the camera rollout, simply enable depth of field, specify the focus distance, and start the render. And all the options are similar to what we discussed in the physical camera, so I'm not gonna repeat myself here. Also, we can produce depth of field as a post effect using the Z depth render element, but we will discuss that in its own specific lesson. And let's take a look at the two final renders. In the first one, the focus was on the clock. And in the second one, it was on the bottle. We also have the denoiser passes, so let's take a look at them too. I'm just going to color correct one of these images here a bit. Maybe let's set the white balance to 7,200. Just making it a bit warmer maybe. Also, let's enable color balance, enable shadows, and make them a bit bluer. Possibly something like 0.10, 12 would work. And the highlights to negative maybe 15. I'm just gonna save these renders out and possibly crop out some sections in Photoshop to make the composition a bit better. There you have it. In this lesson, we learned about depth of field. It's such an interesting concept and has the potential to make the most boring scenes to be so dramatic. So I will see you in the next lesson with the topic of motion blur. Okay folks, in this lesson we learn how to achieve and adjust motion blur in V-Ray. Basically, motion blur is the apparent streaking of rapidly moving objects in a still image or a sequence of images. It happens when the image being recorded changes during the recording of a single exposure, either due to rapid movement or long exposure. When a camera creates an image, that image does not represent a single instant of time, that image may represent the scene over a period of time, right? Most often this exposure time is brief enough that the image captured by the camera appears to be to capture an instantaneous moment, but this is not always so, and a fast moving object or a longer exposure time may result in blurring artifacts which make these apparent motion blur. As objects in a scene move, an image of that scene must represent an integration of all positions of those objects as well as the camera's viewpoint over the period of exposure determined by the shutter speed. In such an image, any object moving with respect to the camera will look blurred or smeared along the direction of relative motion. Let's quickly see what we have in the scene. If I press play, you can see we have these simple animated fan blades. For now, let's go to frame 50 and render our scene from this frame. And the physical camera 02 is the active camera in the scene. In order to enable motion blur, we need to go to the shutter section of the physical camera rollout. So here you can enable motion blur. So let's do that. The reason for motion blur is simply the amount of time that the shutter of a camera is open is long enough to allow your camera's image sensor to see the movement of that object. So longer shutter speed means more apparent and stronger motion blur. Now let's take a look at a few renders with different shutter speed durations. First, set the shutter speed type to fraction seconds, and for the first render, set the duration to 1/1000th of a second. In the first render, motion blur is off, and as you can see, there is no motion blur in the scene. Now, if we take a look at the render with the shutter speed of 1/1000th of a second, because the shutter speed is very short, we didn't capture any movement or any motion blur. For the next render, let's set the duration to 200th of a second. And now, because the shutter is open for a longer time compared to our previous render, we get a slight motion blur in the render. For the next render, let's set the shutter speed to 100th of a second. Again, a longer shutter speed gives us a more apparent motion blur. Now for the next render, the shutter speed duration was set to 50th of a second. More motion blur again, then 24th of a second, again more motion blur. As you can see, longer shutter speed result in a more apparent motion blur because the shutter is open for a longer time and actually can capture the movement of the blades. In the next render, it was set to 4th of a second, and finally a very long 1 second exposure. To recap, and as I'm going through the renders from 1/1000th of a second to a full second shutter speed, you can see a longer shutter speed means more apparent and stronger motion blur. For now, let's set the shutter speed to 24th of a second. The next parameter that we have and can affect the look of the shutter speed is offset, which specifies when the shutter opens relative to the start of each frame. The first render was done with offset set to 0, then 0.5, and finally 1. You can see where the shutter opens at the start, middle, or end of the frame changes the look of the motion blur. For now, let's set the offset to 0 and disable it. There are a few motion blur related options in the render settings, so open up the render setup window and in the V-Ray tab, go to the camera rollout. First, we have camera motion blur, and if enable, the movement of the camera as well as the objects will cause motion blur. We have geometry samples, which determines the number of geometry segments used to approximate motion blur. If you have rotating objects like what we have, or the movement of your object is not a simple linear movement from point A to B, you need to increase the geometry samples to get correct motion blur, which in turn increases the render time because more samples of the object need to be kept in the memory. Now let's take a look at a few renders with different geometry sample values. The first render was done with geometry sample set to 2. Then it was set to 4. Now we get a bit more accurate result compared to our previous render. Then it was set to 8. And finally 16. As you can see, there is not much of a difference between 4, 8, and 16 in this specific case, but for more complex movements you might need more geometry samples. In this case, let's set the geometry samples to 8. And we have pre-pass samples, which controls how many samples in time will be computed during irradiance map calculations. Now, if you don't have a physical camera in the scene and you want to render from the perspective view, which is nothing that I actually recommend, always use a physical camera because it's just going to give you a lot more control. You can enable motion blur here in that case if you don't have a physical camera or if you don't use one. In that case, duration here would control the duration of the shutter speed, which is in frames here. Interval center specifies the middle of the motion blur interval with respect to the 3ds Max frame. A value of 0.5 means that the middle of the motion blur interval is halfway between the frames. A value of 0 means that the middle of the interval is at the exact frame position. Interval center is basically the offset parameter in the physical camera parameters. Bias controls the bias of the motion blur effect. A value of 0 means that the light passes uniformly during the whole motion blur intervals. Positive values mean that light is concentrated towards the end of the interval, while negative values concentrate light towards the beginning. These options are really not that important and you really don't need to change them. And now for the final render, let's set the shutter speed duration to 48th of a second in a physical camera. Now let's take a look at the final render. As you can see, when you have depth of field and motion blur in your render, the render time is going to be very, very long. We have a beautiful depth of field, and the F number for this render was set to 4, and a very nice motion blur. Also, we have the denoiser pass, which uses the mild preset. Let me just turn on color balance and make the shadows a bit bluer. Maybe 0.12, and the highlights can be a bit yellower. Maybe 0.1. So here is our final render with just small color correction. In this lesson, we'll learn about motion blur, and I will see you in the next lesson. In this lesson, we are going to be taking a look at the different camera types available in V-Ray. If I just go to the perspective view and take a look around the room, you can see I've just added a few pieces of furniture to fill the room a bit. Now let me get back to the physical camera 003. To access different camera types, open up the render setup window. Under the V-Ray tab, go to the camera rollout, and here you can find different camera types and adjust them individually. Using different camera types, you can render orthographic views or 360 degrees environments maps or VR ready images. So it's pretty interesting. Let's dig in. Default is obviously the current view from scene camera without any adjustments, and you can see the render with the default type in the frame buffer. The scene was rendered for only 1 minute, and using brute force and light cache, so it's very noisy. Next we have spherical, which uses a spherical lens, and we can use this projection type to produce HDRI environments. What you need to do is to enable override field of view, which override physical camera's field of view, and set the angle to 360 degrees. Also, in the Common tab, make sure you have a 2:1 aspect ratio. In this case, let's set the width to 1000 and height to 500 pixels. And now if we render the scene, we are gonna get a 360 degrees environment map, as you can see in the frame buffer. Then we have cylindrical point. This camera casts all rays from the center of a cylinder. In the vertical direction, the camera acts as a pinhole camera, and in the horizontal direction, the camera acts as a spherical camera. For the first render, let's set the field of view to 65. You can see the render in the frame buffer. And for the next one, field of view was set to 130 degrees. We have cylindrical ortho. This camera casts all rays from the center of a cylinder, but in the vertical direction, the camera acts as an orthographic view, and in the horizontal direction, the camera acts as a spherical camera. And when the camera type is set to cylindrical ortho, we have a new parameter called cylinder height, which specifies the height of the cylindrical ortho camera. In this camera type, we don't have any perspective. Let's set the field of view to 130 and the height to 70 for the first render. And you can see the result in the view, in the frame buffer. In the next render, cylinder height was 140. And for the last render, it was 220. And because the camera is not positioned vertically to be at the very center of the room, we get some of the environment showing up in the bottom part of the picture. And for the final render, field of view was set to 360 degrees and height was set to 140. And as you can see, we get this cylindrical 360 degrees orthographic view. Next we have box, and you can use this camera type to produce cubical environment maps. In the Common tab, let's set the width and height to 1000 and 1000. And if I render the scene right now, as you can see in the frame buffer, we get a cubical environment map. Next we have fisheye, which provides a fisheye lens. This special type of camera captures the scene as if it is a pinhole camera pointed at a 100% reflective sphere that reflects the scene back into the camera's shutter. When set to fisheye, we have a few fisheye related options in our settings. Let me just quote from Chaos Group or Viri's guide for these settings. When fisheye autofit is enabled, Viri will calculate the fisheye distance value automatically so that the rendered image fits horizontally with the image dimension. Fisheye distance controls how far the camera is from the sphere center, which is how much of the sphere will be captured by the camera. And fisheye curve controls the way the rendered image is warped. A value of 1 corresponds to a real world fisheye camera. As the value approaches 0, the warping is increased. As the value approaches 2, the warping is reduced. For the first render, let's set the field of view to 20 and disable autofit. And as you can see in the frame buffer, we get this beautiful fisheye look render. For the next render, field of view was set to 40 and autofit was still disabled. Now for the next render, I enabled autofit and kept the field of view to the same 40. Now the render is fitting properly. For the next render, field of view was set to 80. And in the next one, field of view was set to 120, and because of the characteristics of this camera, we get a flipped image from a certain field of view value. And for the last render, let's disable autofit and set the field of view to 10. Normally you want to use lower field of view when using fisheye camera to get that familiar look to real world. The next camera type is warped spherical, which is the same as spherical camera but uses an older algorithm. Next we have orthographic, which lets us have a non-perspective view of the scene like the orthographic views in 3ds Max. Basically we're going to have a 2-point perspective. All the lines in the view are going to be parallel to their respective axes. To see how this camera works, let's go to the physical camera 004. For the first render, let's set the camera type to default and disable override field of view. And in the frame buffer, this would be the render from the default camera type. But if I change the camera type to orthographic and render the scene, we would get this render. As you can see here, we get an orthographic or a 2-point perspective render. There is basically no perspective here. Now let's get back to physical camera 003. Next we have perspective, which overrides the scene camera to force it to be a pinhole camera. We have spherical panorama, which is a spherical camera with independent horizontal and vertical FOV selection that is useful for generating lat long or latitude longitude images for spherical VR use. As you can see, it's like the spherical type, but we get an extra vertical FOV parameter to control field of view vertically. Let's set the vertical field of view to 180 and override field of view to 360. Also in the comment tab, we need to decrease the height to 500, so we have a 2:1 aspect ratio. And the render would look like this. Next we have cube 6x1, and it's used in generating cubic VR outputs, and the way it works is very simple. You just need to make sure you have a 6:1 aspect ratio for your final images. In the comment tab, let's set the width to 3000 and height to 500, and if we render the scene right now, we get this 6x1 sort of VR ready render. Perfect. So in this lesson, we learned about different camera types. I will see you in the next lesson. In this lesson, we are going to take a quick look at setting up stereoscopic rendering in V-Ray. It's a very simple process to get a basic stereoscopic 3D rendering going on in V-Ray. In the Create panel and Helpers tab, if you choose V-Ray, you can add V-Ray stereoscopic camera helper, or you can do the same in the V-Ray toolbar. So select V-Ray stereoscopic camera helper in the V-Ray toolbar, and click once in the viewport to add the stereoscopic helper. Now let's go to the modify panel and see what we have here. The first thing I want to enable is adjust resolution. Right now the resolution we are rendering with is 800 by 800. If adjust resolution is disabled, the width value will be divided in half for the left and the right eye images. But if enabled, the width value will be multiplied by 2 and each eye image will be rendered in the full 800 by 800 resolution that we have here. Now basically we are ready to render and see the result of our stereoscopic setup. And you can see the result in render 01. To see the actual stereoscopic effect, we can enable stereo mode in the frame buffer. Now we see the left and right images as red and cyan overlays, and if we were wearing proper anaglyph 3D glasses, we would have been able to preview the effect right here. Unfortunately, we cannot save out the render in the stereo mode, and we need to achieve this effect from our raw renders in a post-production application. Let's get back to the stereoscopic helper parameters and see what we have. eye distance specifies the eye distance for which the stereoscopic image will be rendered. 6.5 centimeters is normally a standard value for human eyes. Now if you take a look at the frame buffer and make sure stereo mode is enabled, in the first render eye distance is set to 6.5 centimeters, and in the next render it was set to 13 centimeters. Let's make sure eye distance is set to 6.5 centimeters. Next we have specify focus, which when enabled defines the point of focus with the focus distance parameter down here. We have focus method to specify the focus method for the left and the right views. Let me read you the description for these different focus methods from the V-Rays guide. When set to none, both cameras have their focus point directly in front of them. When set to rotation, the stereoscopic effect is achieved by rotating the left and right views so that their focus point coincide at the distance from the eyes where the lines of sight for each eye converge. We have shear. In this mode, the orientation of both views remain the same, but each eye's view is sheared along Z so that the two frustums converge at the fusion distance. We have interocular method, which specifies how the two virtual cameras will be placed in relation to the real camera in the scene. In the frame buffer, let's take a look at different interocular methods as I explain them. Shift both. In this mode, both virtual cameras will be shifted in opposite direction at a distance equal to half of the eye distance. We have shift left. In this mode, the virtual cameras are shifted to the left so that the right camera takes the position of the original camera. The left camera is shifted to the left at a distance equal to the eye distance. And shift right, in this mode, the virtual cameras are shifted to the right so that the left camera takes the position of the original camera. The right camera is shifted to the right at a distance equal to the eye distance. For now, let's use shift both. We have adjust resolution, which we discussed at the start of this lesson. Let me show you two renders with adjust resolution enabled and disabled again. In the first render, adjust resolution is on, and in the second render, it is off. Let's make sure it's enabled for now. Output layout specifies the format in which the stereoscopic renders are output to the viewer frame buffer, whether side by side or top to bottom. Show cones controls when to show the cones of the virtual cameras created by the stereo reg, which will be discussed briefly later on in this lesson. And in the shade map parameters rollout, you can speed up the rendering of your stereoscopic image. First, you set the mode to render shade map. Then you define where you want to save the shade map. Then you render your scene and the shade map will be saved out. And then you change the mode to use shade map and use the saved out shade map in the shade map file down here and render your scene again. And it will be faster this time. And this shade map file contains basically information about the important visible shaded points in the scene. Reuse threshold affects the rendering with shade maps. Lower values will make V-Ray use less of the shade map and more real shading. The shade map are saved out to 16-bit images. If you turn on 32-bit, they will be saved as 32-bit images. And we have exclude, which allows the user to exclude some of the objects in the scene from being rendered with the shade map. And finally, we get the panoramic pole merging. And if I quote again, the options in this section are used when rendering a panoramic view, like we learned in our previous lesson with camera types, with, for example, spherical panoramic camera. So in this section, the options are used when rendering a panoramic view with stereoscopy. Okay, these options allow us to avoid artifacts when looking upward and downward. This is achieved by gradually decreasing the eye distance and thus the stereoscopic effect. The eye distance value is kept the same until the viewing angle reaches the angle specified in the properties below, after which the eye distance is gradually decreased until it reaches a value of 0 when looking directly downwards or upwards. Those two parameters are top and bottom merge angles, which basically control the viewing angle at which the pole merging effect described above starts. We also have a V-Ray stereo rig which can be created from the System tab. V-Ray stereo rig can be used in cases where the left and right cameras are defined separately. For example, when their animation is predefined from motion capture data. Okay, so we have the left camera, the right camera, and the main camera. Obviously, this was a very brief introduction to stereoscopic rendering, but hopefully it is going to be a good starting point for you. Okay, see you in the next lesson. In this lesson, we'll learn about V-Ray lens effects, which is available via V-Ray frame buffer, and it allows you to simulate camera effects like bloom and glare. To achieve these lens effects, before you start the render, you need to open up the frame buffer. Here you can enable lens effect setting by activating it here. Make sure to enable both bloom and glare effects. Also, another pre-render things you need to do is to enable the intensity for both bloom and glare mask in case you need to use it. And in a moment we learn what intensity is doing. And now you can start the render. As the lens effects are applied after the render and they are a post effect, basically you wouldn't need to render the whole scene just to adjust different bloom or glare parameters again. You can go ahead and render your scene, and after the render is finished you are going to be able to see and adjust the lens effects. Here is our render. For now, let's turn off glare effects and focus on bloom. Let me just disable intensity so we can see the effect a bit better. You can turn on and off the bloom lens effects here. Fill edges, if enabled, will remove the darkening around the edges of the image. We have mode, which specifies to what the effect will be applied. By default it's set to image, and in this mode the effect will be applied to the beauty or RGB color pass only. If set to image and render element, the effect will be applied to the RGB pass, but the effect will also be stored in a render element called bloom. And if set to render element only, the effect won't be applied to the RGB color pass, and it will only be stored in the bloom render element. And you can use this pass in post to produce the same effect. For now, let's set it to image only. Weight is basically the strength of the bloom lens effect. Let's try 0, 20, 40, 60, 80, and 100. For now, let's set it to 40. And size specifies the size of the filter as percentage of the image width. Let's try 0, 5, 10, 20, and 40. Let's leave it at 20 for now. And shape controls the fall off of the effect. Let's see, 1, 5, 10, 20, and 40. For now, let's set the weight to 100 and size to 20. And we get these blurry results because the bloom effect has been applied everywhere. In the bloom mask section, we can define where the effect is going to be applied. Let's turn on intensity and set it to 5. When this option is enabled, the bloom effect will be applied only around pixels that have a value larger than the number specified in the field to the right. Now, as you can see, the effect is only applied to the filament of the bulb. And if you enable object ID and material ID, the effect will only be applied to the objects or the materials with the specified IDs. Let's disable bloom completely for now and enable glare. Also, let's disable intensity for now and zoom in around these bulbs a bit. In the type rollout, you can define how the glare effect is computed. By default, it's set to from render camera. In this case, the necessary parameters like f number and the number of blades are taken from the camera used to perform the rendering and automatically generates the filter kernel. We have glare type from camera parameters, which takes the camera parameters specified in the VRLensEffects render effect itself and automatically generates the filter kernel. Now in this glare type, we can control the f number, the number of blades, and the blades rotation in the camera's parameters section down here. If I set the f number to something like 2, we get a weaker glare effect, and if set to 8, we get a stronger effect. So basically, a larger f number will produce stronger glare lens effects. Now, let's set the number of blades to 3, 4, 5, and 6. For now, I think we can use 4. And you can rotate the blades if you want to, maybe rotate them by 20 degrees here. And finally, we have from image, which takes the image specified in glare image as filter kernel. We can produce these filters using VRLensEffects filter generator. You can find the filter generator in the tools folder of your VR installation. And here we go, I'm gonna open it up here. And the interface is very easy to use. In the upper section, you have the individual components to adjust in 4 different tabs, and in the lower section, you can see the final mixed result of all of those elements basically. Let's create a simple filter here. In the radially symmetric pattern tab, set the value to 15. I'm not gonna change anything in the Corona Flare Lines tab. In the Special Flare tab, let's use 6 ray pattern and let's rotate it by 13 degrees. And in the lower section, make sure to enable Apply Special Flare Pattern. And in the Halo tab, set the inner radius to 41 and outer radius to 86 maybe, and increase the halo to something like 100. Now from the File menu, press Export HDR, use maybe 300 by 300 as the dimension, press OK, and in this case I'm going to save it to the image folder of the project files as glarefilter01.hdri. Now back in 3ds Max, we can load this filter, and as you can see, if we just select it and load it, it basically controls the look of the glare. Let me set the weight to 100 and size to 10 so we can see the exact filter a bit better. Weight specifies the strength of the glare effect: 0, 20, 40, 60, 80, and 100. And size specifies the size of the filter as percentage of the image width. Let's try 2, 10, 20, and 40. For now, change the type to from camera parameters and set the weight to 60 and size to 20. We have turn on diffraction, and when enabled, this produces colored patterns in the glare. As I'm enabling and disabling it, you can see how it affects and basically diffracts the light. And we have use obstacle image, which allows you to draw the aperture shape as well as any dirt or scratches on the lens, which will affect the glare. And in the glare mask, you can define where the glare will be applied based on the intensity, object ID, or material ID. And finally, in the update control section, you can define whether to interactively see the changes you apply using these parameters or see them manually each time if you disable this value. And finally, let's make sure intensity is disabled, set the weight to 80 and size to 5. I mean, we can disable bloom, but for here, let's maybe enable it, set the weight to 50, size to 5, and maybe shape to 4. Make sure intensity mask is disabled. And here is our bloomy, glary image. I think we can even disable bloom, which is what I'm gonna do for this final render, which was done in a high resolution. And this is the final render. Maybe we can adjust it, but I'm gonna let you do that on your own. Okay, in this lesson we learned about VRA lens effects, and I think we are done with camera section. I'm gonna just check my outline out and see if there is anything remain to discuss for this section, and if not, I'm gonna see you in the next section, and if there is anything to talk about, I'm gonna see you in the next lesson. Okay, in this last lesson, I'm gonna be discussing creating V-Ray physical camera and also exposure control in your render if you don't have a 3ds Max or a V-Ray physical camera in your scene, or maybe you have a camera in your scene, but in order to analyze your scene, you try rendering from multiple perspective views and you want to have some sort of exposure control in your scene. So if you open up the environment and effects window from the rendering menu, or just press 8, we have a section called exposure control. Right now it's set to physical camera exposure control, and in the physical camera exposure rollout, use physical camera control if available is enabled. Therefore, if we are viewing the scene through a physical camera, the exposure controls from that camera will be used. Right now we have no camera in the scene, so we can control the exposure of our render through the global exposure parameters down here. We have the exposure value. If I render the scene right now, you can see from the light cache preview it's a bit overexposed. So stop the render, and this time let's set the exposure value to something like 10 and render again. Now you can see from the light cache preview that we have a well exposed scene. Also, we can control the white balance like we did in the physical camera. So if I use temperature and set the temperature to something like 3500 and render the scene, as you can see, we get a very cool render. Let's for now set the temperature to 6500 and enable illuminant again. We also have some other controls down here. Instead of physical camera exposure controls, we can use V-Ray exposure controls, and now we have a very simple and familiar set of parameters to control the exposure of our scenes like we would have done if we were using a V-Ray physical camera. First, we have mode, and right now it's set to photographic, so shutter speed, f number, and ISO will affect the overall exposure. If I set the mode from EV parameter, the exposure will be controlled by this single exposure value here. If I render the scene right now, you can see it's fairly well exposed. If I set it to -5 and render the scene, you can see we have an overexposed render. And if I set it to +3 and render again, the scene becomes underexposed. You can see the way exposure value works here is a bit different compared to the one in the physical camera, but they are doing the same thing. And we have from V-Ray camera, and in that mode you specify a V-Ray physical camera in the camera node here, and the exposure settings will be taken from that camera. You can render your scene in any perspective view that you want, but the exposure settings will be taken from the specified camera node here. And down here you also have some white balance controls. You can use some presets like neutral and daylight, or you can set it to temperature and use any temperature to control the white balance, or use any custom color. And one final thing, if you are craving a VRay physical camera and you want to use it instead of a 3ds Max physical camera, what you need to do is to open up the Max script listener and run this simple command: VRay create VRay physical camera. And let me just copy paste it here and press enter. Now we have a new VRay physical camera in the scene, as you can see in the Explorer here. Let's select the camera, press Ctrl C so the camera adheres to the current perspective view, and then press C to see the scene through this new VRay physical camera. And if you go to the modify panel, you can see we have all of these camera settings. Maybe the layout is a bit different, but we discussed these parameters in the 3ds Max physical camera, and they are doing pretty much the same here. And I suggest that you use 3ds Max physical camera in your scenes instead of VRay physical camera. Okay, perfect. So in this lesson, we learned about exposure controls and how to create a VRay physical camera. I will see you in the next section.